All right, everyone. We're going to now talk about the last and final lecture, which is friction and tipping. What we've already discussed is this guy over here and how when he pushes a box, how friction is involved in trying to prevent his ability to move that box to the right. But what we're going to also talk about now is that this guy, if he pushes the box, not only could it slide, but it could also tip. Check out that awesome PowerPoint animation. Going to get the Academy Award for that one. Let's do it again, just so you can see how awesome and impressive that was. So the guy can push and slide things, but sometimes also he can push it over. Wow, amazing. Okay, why is this relevant in the real world? Well, slipping and tipping is very relevant because if you're driving a car down the road, I think you'd much prefer your car to slide down the road to a stop rather than to tip over and enter into many rolls down the street. That would not be particularly fun. Also, if you're trying to do construction work and you don't have your statics right, it's very possible that you're going to end up doing a lot more construction work than you originally intended. And that wouldn't be very good either. Lots of famous things in the world tip. We have the Leaning Tower of Pisa, which lots and lots of people go and take pictures and selfies with, doing all sorts of fun things. And, really, this was one of the first designs that actually had people realize that geotechnical or soil engineering was really important. Now, you might think that we as a society have gotten smarter and better and can prevent these things from happening. Well, you'd think wrong. Very recently, a 58-story skyscraper in San Francisco called the Millennium Tower, which cost over $350 million, has already sunk over 16 inches and tilted several inches since it opened. You can imagine that in a very seismically active region, that's probably not very good. Now, the fun and probably really bad news, but also really interesting thing, is that in order to fix it, engineers are thinking it may cost over $500 million, which if you look at that, that's pretty mind-blowing because the building itself only cost $350 million to begin with. So you got to do your engineering right and you got to make sure you're accounting for the tipping of things as well. So what are we going to cover in our lecture today? Really, we're going to cover this problem right here, a basic introduction and overview of what tipping is all about. When you apply a force to an object, you're either going to cause it to slide or you're going to cause it to tip over. And generally speaking, in friction tipping problems, you're going to be trying to find out which of these two things is more likely to occur. Is it more likely that the block will slide, or is it more likely that it will tip? We'll then move to a slightly more sophisticated example with an inclined ramp and a non-tangential force to our object, answer pretty much the same question. And then last, we'll finish with a question that has two objects or a composite system. And we'll discuss what possibilities there are in a system like this and how to solve this type of friction tipping problem.
Oh, hello ENES 102 students. Didn't even see you there. Just Mike here. Actually about to head off to, actually nowhere. Pretty much all of my travel plans have been canceled for the foreseeable future. So, since I've got this suitcase conveniently here, and we just happen to be on the friction tipping lectures, I'll teach you a few things. Pretty much in this lecture series, what we're going to be discussing is when you push on an object, what happens? Does the object slide like this rolly suitcase is intended to do, or will that object tip? Now, if you were to tip me, which I would very graciously accept some tips via my Venmo account for all this work I've done over the course of the semester and all the baked goods, but no worries. But if I were to tip, if I moved back, if you were to push me, and I were not to slide, which we're on a concrete floor, I've got my boots on, it's very unlikely. What you would see is that I would start to kind of put all of my weight on my front right foot as I began to fall to the right. That's exactly what happens in a situation when you've got friction and tipping, particularly for this suitcase. So let's see what happens. Let's do some demos with this suitcase to understand how friction and tipping works. first thing we want to look at is the geometry of our suitcase. It's a rectangle, so we know that the center of mass is going to be located somewhere in the middle. In this case, because we've got these wheels down here, maybe even a little lower. Now, the factors that are going to influence whether this suitcase either slides or tips is what we're going to look at right now. So, the first thing we can do is let's apply a force down here below the center of gravity and see what happens. Our suitcase rolls away just as we expect. Okay, what will happen now if we apply a force to the top of the suitcase above the center of gravity? We'll see now. Our suitcase still rolls, which is pretty much what it's designed to do. But let's see if we change one other thing. Alright, what I've done now is extended the handle up so we can apply a force even farther away from our center of gravity. Now let's see what happens. Okay, now the suitcase still rolled, but something different happened. What you could have seen was that the suitcase, while it was rolling, began to tip a little bit about the very front wheel, and then it slid. So one thing that we can see is happening is that as we raise our force higher away or above the center of gravity, we're more likely to cause the object to tip, which that makes sense. Objects that are taller are going to be easier to tip over. Now let's look at another aspect we need to look at when friction and tipping. Alright, now the other factor we're going to need to consider in friction and tipping is the coefficient of friction between the floor and our object. Now I've moved the suitcase away from our concrete and put it onto grass. The reason being that on concrete our wheels can move very well, but on grass, not so much. So, now if I apply a force to the bottom of our suitcase, it still rolls, but it doesn't slide away like before. So we can see that the friction coefficient is much higher. Now look what happens when I apply a force to the top of the suitcase right here. Before, it just slid. Let's see what happens this time. Now, what you clearly just saw is that the suitcase rotated and fell over about the front wheel. So what happens in tipping is that the normal force goes exclusively to the front wheel, and the normal force in the back wheels goes away as those begin to tilt over. So we just learned now there's two factors that matter. One, how high we apply our force to our object, and two, the coefficient of friction. There is one other factor that's going to matter. What we can see is that if our center of gravity is here, when I push on our bag, it begins to rotate. But when I let go of the bag, what happens? The bag corrects itself and rotates back towards me. The reason is that my force causes this bag to rotate counterclockwise, but the center of gravity is applying a moment relative to that wheel to cause it to rotate clockwise. So what you can estimate is that if this suitcase got wider and wider and wider this way, the weight would actually be causing a greater and greater resistive moment to rotation. So if I rotate the suitcase this way, what you can see is that even if I apply a force pretty much just at the center of gravity, I cause the bag to tip over so easily because it's very, very narrow. So the resistive moment applied by the gravity is almost zero. So that's the three factors that matter. The height of our force, the width of our object, and third, and really the first thing we talked about, the frictional coefficient between the ground and our object as well. Let's get back to the lecture.
Okay, everyone. So what we're going to do now is we're going to look at the way to model a slipping or tipping problem and determine whether or not when you apply a force to a block, whether that block will slide. So right here I've got my calculator top. And when the calculator top slides, the motion would look like this. And when it tips, it'll be tipping about the front right corner, at least in this particular problem, and it'll look like that.
So how do we determine which of those two motion cases is going to happen? Well, that's what we're going to find out. And in this particular problem right here, you can see we've got block A, we've got its width and height dimensions, and we've also got the location that the force is applied relative to the ground. The question is asking us, as most friction tipping problems will the block slip or tip first? So essentially we know that as we apply this force, as this force gets larger and larger and larger and larger, this block is either going to slide or tip over at some point. And the question is, which of those things is going to happen first? Now the givens are that we've got the coefficient of friction between the block and the floor, 0.75, and the weight of the box is 10 pounds. Our question is, what is the force applied? So the way that we approach all of these problems is we have to break it into two parts. Part number one is usually to look at the slipping case. And in the case of slipping, this will occur when the force applied exceeds the force of friction maximum, which is what we talked about in our force of friction lectures. So the way to do this is to draw a free body diagram of the block in this particular scenario. Now, this free body diagram is pretty straightforward, and you should all be free body diagram pros at this point, but we'll draw it anyway. So we've got the weight at A, we've got the normal force acting on the block down below through the centroidal axis, and we've got the force applied over here. This is at 5 feet. And last but not least, we've got the force of friction acting along the bottom of the box. Last few things we need to do just to make this a complete free body diagram is add our 2 feet dimension there, our 6 feet dimension here. And of course, XY axis. Got to get those freebie points. Okay, so looking at this isn't particularly challenging. We know that what we're trying to figure out is the balance between force applied and force of friction. So really the question we're trying to answer here is, what is the force of friction maximum? Well, we know that the force of friction maximum is equal to mu s times n. Now, we know mu s, but at the moment we don't know the normal force. So that's why the first step we have to do is to sum the forces in the y, set that equal to 0, and this equation is going to tell us that the normal force minus the weight of box A must equal 0. Therefore, this should come as no surprise to us, but the normal force is equal to 10 pounds. Now, we didn't really have to do this to figure it out. You shall be pretty smart at this point, but we just did this just to get our points and make sure that we're following proper procedure in the case that the problem becomes more complicated. So we've got our sum of the forces in the y, we've got our normal force, and then therefore our sum of the forces in the x direction, just to double check, is equal to 0, is going to be equal to our force applied minus the force of friction maximum. So what this is telling us is, again, that the force of friction maximum is going to be equal to the force of the applied force in the case of slipping. So pretty much what we can determine from this is that Fa is equal to mu s times n, which is going to be equal to 0.75 times our normal force, which is 10. So I like to say that Fa to cause slipping is going to be equal to 7.5 pounds. This is our first applied force that we've solved for. The second step that we're going to do in these friction tipping problems is that we're going to try and solve to see what force applied would cause this box to tip over. So how do we do that? We actually have to draw another free body diagram. And the way to approach a tipping free body diagram is to actually look at how this box would tip. If this box is tipping, it'll be tipping about this bottom point, which we usually refer to as A. Now, what this means for us is that when we draw our free body diagram, we want to draw our box at a very slight angle. So slight
that you basically can't even see the angle between the box and the ground. So realistically, what's happening in tipping is that our box would go like this. It would tip over, and all of the force of the normal force would be concentrated in this point. What we're doing is we're going from this free body diagram to this free body diagram with a theta equals 0.1 degree, basically. That way we can keep all of our geometry looking nice and straight, because if we draw something that looks like this, we'll start to get all confused, and that'll make us really sad face. So we want to keep it like this, and the way that our free body diagram is going to change is we still have the weight of the box, WA. We still have the force applied. And now the only difference is we're going to have the normal force only acting at the front right, because that's what would happen in the case of tipping. And of course, we still have the force of friction acting down below. Now, let's just do this problem in terms of generic numbers first. So we've got the weight of the width of the box. We've got the height in which the force is applied. So what's going to effectively happen in a tipping problem is that tipping will happen when we've got a net positive moment about point A down here. So essentially, the moment of FA is going to be greater than the moment caused by the weight of the box. So when we write this out for tipping, we're going to write the sum of the moments about the place where it's going to tip, which is point A, the front right corner. So when we do this, what we'll see is that we've got one force that's causing it to tip, which is F applied times H, minus WA, the weight of our box. And I actually kind of sometimes like to say that this is mg, just so we don't get confused. But this is mg times the moment, which is going to be the width of the box, over 2. So when we get a generic equation basically to find F applied to cause tipping, that's going to get us mg times W over 2 divided by H. Now let's look at this equation for a second and kind of see what's going on. So you can see that if we were to make our box wider, it'd be a lot harder to tip. You know, something that's low and wide is going to be very tricky to tip over. You can imagine that if I had this box right here and I tried to tip this over, I have almost zero chance of tipping this if it were on the ground. But something that when it's like this, it's much easier to tip this shape when it's like that. So as the width goes up, the force applied goes up. And as the box gets heavier, the same thing is going to happen. Now, the force is applied at a height h. And you can imagine that the higher we apply this force, the more likely our object is going to be to rotate. So, if we increase the height of this force, we'll actually decrease the force necessary to cause tipping. So really, something I want you all to write down, and probably this is one of the main things you come out of this, at least for a simple box problem, is that our FA tip looks something like this. So, when we plug in the things that we have for our problem right here, we know that the weight of our box is 10 pounds. So we plug in 10 pounds. We know that the width is 2.
So we have 2 over 2, and the height in which our force is applied is 5. So this tells us we have 10 times 1 over 5. The force to tip our box is going to be equal to 2 pounds. So let's go back and answer our main question. Will the block slip or tip first? What we can see is that FA tip, which is 2, is much less than FA slip, which is 7.5 pounds. So our box is going to tip. And FA, maximum that can be applied, is 2 pounds. So what does this basically mean? It just more or less is the limiting factor. So when I've reached 2 pounds, my box will start to tip. In order to cause my box to slide, I would have to apply at least 7.5 pounds. But to apply 7.5 pounds, I would have already caused the box to tip because I would have exceeded this value of 2 pounds. So that's how you approach a very straightforward friction tipping problem with only one particular object. Now, things that can change, you could have multiple forces in the system, you could have the block be at an incline, and what we'll start to do as we move later on is we'll start to discuss systems where you have more than one block and possibly other things involved, like a rope or things like that. But for now, that's it. That was our introduction to a friction tipping problem. Okay, everyone, now what we're going to do is we're going to look at another friction tipping problem where we've got just a little bit more complexity involved. But as you'll see, the steps that we follow to solve this problem are going to be pretty much the same exact steps that we took just a moment ago to solve the last problem. So pretty much what we've got going on is we've got this refrigerator. Someone's pulling it at the top with this rope. The rope is pretty much attached right here. It kind of looks like the rope goes around, but we're going to ignore that and treat it as if this force is applied at the top right of the refrigerator. We can see that the fridge is inclined at an angle of 20 degrees. And what we can pretty much see is that the refrigerator is a mass of 75 kilograms. So the mass of one average human being, 150 pounds, acting through point G. We're told the ramp is inclined at 20 degrees and the coefficient of static friction between the refrigerator and the ramp is 0.3. So that's the only one we're going to have to worry about. Our question is, find the force required to move the refrigerator, and does the refrigerator tip or slide? So the question is effectively the same. We're looking for F applied to cause motion. And we have to determine whether the fridge will slip or tip first. So just like in our last problem, there's two cases we have to consider. Case number one is going to be slipping. That's always the case that I check first, just because it's usually the easiest case to check. So when we draw our free body diagram for slipping, not particularly hard. We draw our ramp, we draw our angle, and now we'll draw our fridge. Now in this particular problem, we want to make sure that we have all of the appropriate dimensions on our fridge. So we've got 0.3 and 0.3. We've got 1 meter, 2, the fridge's center of gravity, G, and we've got 0.5 meters from there to the top. Now, the forces that we're going to have acting on our fridge are the following. And this is where things get a little tricky. But basically, let me draw this a little bit more clearly and with a different colored marker so we can see it. You can see that our force P is applied just straight horizontally out like this. So what you can kind of see as a result of this is that this line right here and this line are parallel, and the P and our force down here are also parallel. So what that tells us is that this angle right here is theta equal to 20 degrees. That's probably the trickiest part of this whole problem, honestly, is figuring that out. Lots of people don't see that very clearly, but hopefully what I just showed you makes sense. The next thing we're going to have to draw is the normal force. The normal force acts straight through the refrigerator, right here, through the center of gravity. And the other force we have to draw is the weight. Now the weight of the refrigerator is like this. So the weight is going to have two components. It's going to have a component that acts into the ramp and a component that acts down the ramp. And we'll define those later, but we know again that this is theta. And it's the same theta as we have over there. So I'll just even write that here. Theta equals 20 degrees. Okay. Now we've got our force applied, we've got our weight, we've got our normal force. We're missing something. Well, the thing we're missing is the force of friction, which is going to be acting down the ramp this way. Okay, now remember, I told you that slipping will occur when force applied exceeds the force of friction max. But really, it should also be saying when it exceeds the force of friction max plus other resistive forces. So in this case, to move the refrigerator, we not only have to overcome friction, but we also have to overcome the weight of the refrigerator moving down the ramp. So what we do here is we draw our XY axes this way, because that is usually pretty helpful. Okay? And we have to now sum up our forces in the X and Y direction. So let's look. We've got our sum of the forces in the X direction. We know that that's going to be equal to 0, which is going to get us our P cosine 20 degrees. And that's going to the right, so we say that's positive, minus mg sine theta. So that's mg sine of 20 minus mu s times n. Because again, we're dealing with force of friction maximum. And it's probably a good idea just to make sure you remember that in these problems, the force of friction we're dealing with is going to be the force of friction maximum. So in this particular problem where it's asking us how much force to move the fridge, we know we have to apply at least mu sn to exceed that. So when we look here, we don't know P. We know mg, we're good there, but we don't know n. So this is where we have to do a sum of the forces in the y equation just to prove that we know how to do some statics. And our sum of the forces in the y is going to give us the normal force up minus mg cosine of 20. That's this component right here. And now we also have P comes into play. That's why this is actually a little bit trickier. And our P is going to be going down this way. So we have minus P sine of 20. Now what you can see going on is, look, we've got two equations and two unknowns, the normal force and P. So what we have to do is we do a sum, pretty much system of equations. And from this equation down here, we can say that n is mg cosine theta plus P sine theta. If we take this and we plug that back up into here, what we'll basically get is that P cosine 20 minus 75 mg times 9.8 times sine of 20 minus mu s times n. Well, this is what we have for n. So pretty much what we're going to get is minus mu s 0.3 times mg 75 times 9.8 cosine theta. So we're distributing the
mu, which is 0.3, to these terms right here from over here. So now we're going to have 0.3 times p sine theta as well. But remember, it's negative because of this negative sign over here. So we have minus 0.3 times p sine of 20. And this whole equation is equal to 0. And this, again, is just from the sum of the forces in the x. Now we've got everything we need to solve for p. And when we solve for p, what we get is that p is equal to 545.5 newtons. And I like to say that this is called p tip. So the force required at the top of this refrigerator to cause it to tip over would be 545.5 newtons. Now what we're going to do is we're going to look at how to calculate tipping for this problem. And I'm going to open up another sheet so that we have more room and it's a little bit easier for you to see what I'm writing. All right, so I've started our new sheet here, and I've pretty much started off drawing our free body diagram again. And our free body diagram is going to be pretty much the same as it was in the last instance. But remember that for tipping, we're going to be tipping about this front right corner, which we usually call point A, or at least I am in this problem. And if we're tipping about that point, that means that all of our weight is going to be shifting to that point. So our normal force no longer acts in the center, but our normal force acts at the front right corner now. So now what we need to do is we need to determine pretty much a sum of the moments about this point A, which is the point we're tipping about. So our equation for this problem now becomes that the sum of the moments about point A must sum to equal 0, which is going to give us mg cosine theta, which is this component, times 0.3. That's our first thing that we're going to include. So mg cosine theta times 0.3. This is going to cause things to rotate counterclockwise. So this is positive on our coordinate system. We're also going to have this mg component going down the ramp. And remember that in these particular types of problems, you want to draw it that way, at its actual location. And that is also going to cause things to rotate counterclockwise. So this is going to be plus mg sine of theta times 1. And last but not least, we're going to have to account for the effects of p. Well, this vertical component of p looks like it's having something going on in this problem, but remember, this p is really acting from this point. So that p would actually go through point A. So we don't consider py, we only consider px. Well, and I'll just draw py here as well so that's clear. So we only consider px, which is p times the cosine of 20, and that's the tipping force. That's what's causing this to rotate clockwise. So you can see our weight is acting counterclockwise. It's causing this fridge to want to rotate to the left, and our p is what's causing the fridge to want to rotate to the right. So we now have minus p cosine of 20 times, well, the total height, 1.5. Now from this equation, what you can see is we know everything here. The only thing we don't know is p. So when we solve for p tipping, what we get is equal to 324.23 newtons. Okay, so our question is now answered pretty much. We just have one final step. We need to determine, does the refrigerator tip or slide, and what's the force required to move it? So we said that P tip was 324.23, and from before, we had that P slip was equal to 545.5 newtons. And I think I might have made a mistake on the last page and I said that that was tipping, but that was slipping. So sorry about that.
what we can see is that P slip is 545.5 newtons. So which of these things is going to happen first? Well, because P tip is less than P slipping, the answer is that P tip will be the thing that happens. Our refrigerator will tip. And our final answer is that the maximum force applied is 324.23 newtons. And that's it. That's how you approach another friction tipping problem, albeit, again, with only one object, but with some different things going on. A force that's not perpendicular to our object and on an incline. Now what we're going to do is we're going to look at another problem in a little while that has two objects. And that becomes quite a bit more complicated in how you consider what's going to happen in that problem. Okay, now what we're going to do is we're going to solve a problem in friction tipping that involves two objects and a guy with a really freaking cool hat. Check that hat out. Super retro. That is straight fire. Oh yeah. He's not on fire. That's probably going to be confusing in the future when fire is no longer a cool word. But anyway, here's what we got going on. We've got a carpenter. He's slowly pushing this uniform board across the sawhorse. Now, some of you probably got excited and were like, woohoo, seahorse. I love seahorses. But, sorry, it's a sawhorse. The idea is it's there to keep this board balanced. We're told that the board has a uniform weight of 3 pounds per foot, and the sawhorse weighs 15 pounds, with its center of gravity at G, as shown. So we kind of know everything we need to know about the sawhorse. We've got all this detail about the board. We don't really know anything about the carpenter. Let's give him a name. Let's call him Bob the Carpenter. Because why not? So let's say that Bob is pushing this board over here. And the question really is what's going to happen or what's possible to happen in this case? Now there's two things that we can actually have happen. Well, three things actually that can happen here. So let me get my handy dandy TI-83 calculator. So this down here is like our sawhorse, and this up here is like our board. So what can happen is if I push the board can slide over top of the sawhorse, and the sawhorse can remain stationary. What can also happen is if there's enough friction between these two surfaces, but very little friction on the floor, it's possible that both of these things actually move when I only push the top one. Alternatively, what can also happen, now in this particular case with the TI-83, these are both pretty tall shapes. So it's possible that this shape here could actually tip, and in theory it's also possible that both shapes could tip simultaneously. So in a normal composite problem where you've got kind of two larger structures, there's 4 cases that you would have to check. In our case, if we go back and we look at what's happening, we can see that we've got a board, so that can slide over top of the sawhorse. And you might say, oh, couldn't the board tip as well? But something you can notice is that we don't have a height for the board. We're assuming that the board is super small, which it's probably about 1 inch or so, which it's not going to be able to tip as a result of not having any height. Because remember that our equation for tipping involves how high we're applying the force relative to the object to cause it to rotate. So anyway, the only thing that this board can do is slide. The sawhorse, on the other hand, can do 2 things. Because it has this extra height of 3 feet, the sawhorse can slide with the board, or the sawhorse could be tipped by the board as well. So you can see this problem is a lot trickier than the ones we've done so far. And really, there's 2 different things that can happen. Now, what we're going to do is we're going to draw 2 free body diagrams, 1 for each shape. And we're going to draw those just right here and get things started. So, step 1, we're going to draw free body diagrams. And maybe what we'll do first just to make sure we've got enough room on our paper, is I'll draw a free body diagram for our board. So we'll evaluate what's going on at the board, and then on the next page, we'll evaluate what's happening with the sawhorse. So draw a free body diagram of our board that good old friendly Bob the carpenter with his fire hat is pushing. So here's our board. We can see that our board is 18 feet long, which tells us that its center of gravity, G, is going to be at 9 feet from the edge. So we'll say here's the weight of the board. And then here is the force applied by good old Bob. We call this F push. And what we can see is happening is that the sawhorse is going to be applying a normal force at this distance D. And we're told that D is 10 feet. So we'll just put this D right here. Or sorry, normal force of the sawhorse on the board. Okay? And we'll say that this is 1 feet away from our force over there. The last thing we have to draw here is, you guessed it, the force of friction. So the force of friction will act right there. And that's pretty much all we need at this point in time. One other thing we might want to draw here is just this dimension, just so we have everything we need. And really, again, the only thing that can happen on our board is to evaluate the tipping. Or sorry, evaluate the slipping. Because those words rhyme, it gets very tricky, and it's very easy to make a mistake saying one versus the other, so I'm sorry. So we're evaluating slipping for the board. So effectively what we've got to do is say the sum of the forces in the x is equal to 0, which tells us that F push minus the force of friction, and we'll call this the force of friction at point B, the force of friction on the board. This has to equal 0. So to get this board to slide, we know that F push is going to be equal to mu s times n of the sawhorse on the board. But at this moment, we don't know the normal of the sawhorse on the board. It might be tempting to say, oh, normal of the sawhorse on the board is going to be the weight. And that's exactly what the person who wrote this problem wanted you to do, and to fall into that trap. But look, these things are offset. They don't pass through each other. So we can't just do a sum of the forces in the y direction equation to figure this out. We actually have to do a sum of the moments equation to figure this out. So what I've done is I'm calling this point A, which is the contact point with the sawhorse. So the sum of the moments about point A is going to be equal to 0, is equal to the weight of the board. Now, what is the weight of the board? What we're told is that the weight of the board has a uniform 3 pound per foot. So really, we were given like a distributed load on top of our board. And the way that we figure out the weight of the board, I'll do it over here, is that the weight of the board is going to be equal to our 3 pounds per foot times 18 feet. So that is 54 pounds. And this is effectively like F equivalent of our rectangle. Okay? So what we have relative to this point we're doing our moments about is we're going to have the weight of the board times 1. So we're going to have what we're doing actually is this isn't point A. Point A is this end over here. This is nothing. This is just the contact point. So our point A is over here, because if we sum the moments about this point, then the only thing we would have is this weight right here, which wouldn't work out. We're trying to solve for this force right now, NSB. So when we do some of the moments about this corner over here, we have weight of the board times 9 is going to be clockwise. So we have minus weight of the board times 9, plus NSB times 10. Because we know that the weight of the board is 54 pounds, what we can do is solve for NSB, and we learn that NSB is equal to 48.6 pounds. Okay, so F push is going to be equal to force of friction maximum. We're told that the coefficient of friction between the sawhorse and the board is 0.5. So we're going to have over here, mu s is 0.5, and NSB is 48.6 pounds. So the force of friction maximum is equal to 24.3 pounds. And this would be the force to cause the wood to slip. Now this was just the first condition we were checking. We're going to have to check 2 more conditions for the sawhorse, both slipping and tipping of the sawhorse. And I'm going to start a new sheet of paper and get us started working on that problem. Okay, now what we're going to do is we're going to look at the sawhorse. And the first step is to draw a free body diagram of our sawhorse. So we were told where the location of the center of gravity of our sawhorse was. It's right here, located at G. So the first thing we're going to draw here is the weight of the sawhorse, WS. The next thing we need to do is we need to understand that the board is pushing on the sawhorse down. So we've got N of the beam on the sawhorse, NBS, Newton's third law pair from before. We know that we've got normal left and normal right on the sawhorse. And technically speaking, we're going to also have frictional forces on both of these legs. Force of friction left and force of friction on the right leg. The last thing we have to do is we have to put this force of friction from the previous problem here, force of friction from the beam. Because remember Newton's third law, if the sawhorse is applying friction to the beam, then the beam is also applying friction at this contact surface right here. Now, the only other things we need to do are draw some dimensions. So we've got 1 foot right here, and we've got 1 foot right here, and we know that our sawhorse is 3 feet tall. Okay, that's it. Now for our sawhorse, there's 2 conditions we need to check. So condition 1, say 1S for the sawhorse, we actually luck out for the S is going to be slipping. Now how do we do this? Effectively, we write a sum of the forces in the X equation. So we say sum of the forces in the X is equal to 0, is going to be equal to FFB, the force of friction from the beam, which we already technically have, minus the force of friction on the left leg, minus force of friction on the right leg. So that's the 3 things that we have. Now we know that in order to cause this to slide, both of these things have to be the maximum friction. So this equation can be rewritten as FFB minus mu s and L minus mu s and R. Now because these 2 things are the same, right here, the mu s, we can factor it out. And this will actually be somewhat helpful in a second. So because we can factor that out, we get the equation that the force of friction of the beam necessary to cause us to slide would be equal to mu s times NL plus NR, which is equal to 0.3 times NL plus NR. Now we don't really know the balance of these 2 things yet, so we have to check something. What we're going to do is just do a sum of the forces in the Y just to see what these are.
So we know that the sum of the forces in the y is equal to 0 is equal to NL plus NR minus the weight of the sawhorse minus NBS. Now remember, we saw for both of these things before. On the last page, we said that NBS was 48.6, and the weight of the sawhorse is something that's given, and that's 15. Now the reason why I factor this out up here is because something you can see in our sum of the forces in the y equation, we would have technically had two unknowns. So I would have had to do a moment equation or something like that, which would have gotten a little bit tricky. But conveniently, I can now bundle these two variables right here as a single variable. And what I get is that NL plus NR as a unit is equal to 15 plus 48.6. which is equal to 63.6 pounds. So now what I can do is I can go back up and apply that to this equation so that the force of friction of the beam, which is essentially F of the sawhorse to slip, is equal to 0.3 times 63.6, which is equal to 19.8 pounds. Now let's look at what we had on the last page and see how this force compares. From before, we'd calculate that the force required to slide this piece of wood was 24.3 pounds. But the force to cause the whole system to slide is 19.8 pounds. So what we can see right now is that this is what's governing it. And one of the reasons why we can see this is that the ground has less friction than there is between the board and the sawhorse. So before the board slides, the whole system starts to slide because the ground has less friction. So right now this is our limiting factor, but the question will then become, maybe our sawhorse tips before it slides. So that'll be the next condition we check. So the last thing, condition 2, which is tipping. Okay. We know that our sawhorse is going to tip about this front leg. And we're not really given a thickness of the leg, so this kind of picture is a little bit inaccurate. So we're just going to assume that this is kind of our pivot point. And what we're calling this point right here is point B. So if our sawhorse tips, it's going to tip clockwise about this front leg right here. So the only thing we need to do is sum our moments about point B, which is the front leg, set that equal to 0, and that gives us FFB times 3 clockwise minus NBS times 1. And what I'm doing is I'm basically saying our tipping force is the positive force. So I'm just saying clockwise here is positive. And then we've got NBS times 1. So minus NBS times 1 minus the weight of the sawhorse times 1. Now, NR and the force of friction go away because they pass through that point. And the things over here also go away and are not in our equation because the left leg isn't even touching the ground anymore once it starts to tip. Okay? So we just have this equation right here. So when we calculate FFB, we're really calculating F tip, which is going to be 48.6 plus 15 divided by 3, which is the simplification of what we get from all of our math above. So when we do this, we calculate that F of the sawhorse tip is equal to 21.2 pounds. So
So that would be the force up here, FFB, which we're treating pretty much as F applied. So this force would need to be 21.2 pounds to cause it to tip. But we see right here that if this force were 19.8 pounds, this whole system would slide. So because 19.8 is less than 21.2, so we have 19.8 is less than 21.2, and this is the sawhorse slip condition is less than the sawhorse tip condition, and this is less than what we calculated on the last page, which was the 24.3 pounds, which was the board slipping. The thing that governs our entire equation is 19.8 pounds, and that's the maximum force our person can apply, good old Bob the Carpenter, can apply before anything moves, and it'll move as a whole system sliding to the right. And that's it. That's how you approach a composite problem, and this one's pretty good, and then it covers almost everything. The only thing we didn't really do, because our board didn't have height, was check to see if the board would be rotating around. But we'll work on one of those problems again at some point in the future. The middle. Now if I push very low on the suitcase, you can see, whoops. Oh no, wheel fell off? This is what happens when you push a suitcase too hard. Its wheel falls off, and that's why it just fell over.